Let's quickly touch on some of the things we've already talked about, like Coriolis effect. This shows it more explicitly. On the equator, you are moving linearly, and because it's much larger, and you're covering the distances in 24 hours at all latitudes, obviously you have to move much faster here at 500 meters per second, and it decreases as you go to higher latitudes, but not linearly. And obviously Santa Claus up here is not moving and just spinning, going ho ho ho, Merry Christmas. It's actually the day after Christmas as I'm recording this. So the main thing we want to remember without going into the details is that in the northern hemisphere, no matter in which direction you want to move, if you move at planetary scales, you're going to be tilted to the right of the direction of motion by Coriolis. In the southern hemisphere, things are the other way, so you get tilted to the left of the direction of motion. And you can look at my podcast on Coriolis on my channel as well for further details. This is showing again the cells we looked at, but now with precipitation and more details. Here is our maximum heating, convergence of the northeasterlies and southeasterlies with mid-latitude westerlies. Where the Hadley cell sinks, you get the high pressure subtropical gyres, deserts, no rain, high pressure, no rain, low pressure, rain. So you can see the mid-latitude storm track here broken into these low pressure cyclonic systems, and the wind direction shown here is different than before, where typically we talk about Hadley cell, Ferrel cell, and polar cell, but actually there are additional dynamic complications because of the angular momentum that's very large here. If you move air northward, then it goes unstable, breaks into these kind of cyclonic systems, baroclinic instability in particular, and so on. And you get a front there where there are also rainfall. So you can see that there is rainfall in the latitudes where ITCZ hangs around. Evaporation is happening in the mid-latitudes and supplying the Hadley cell and the rising air. So moisture and air is being supplied in. And here you have convergence of the cold front and the warm front, so you get a different kind of dynamics here to produce these storm tracks. So you get rainfall over there as well in both hemispheres. They're not perfectly symmetrical, as we already talked about, and as we will see here. So this is showing June, July, August, and December, January, February. So in this is December, January, February, and this is June, July, August. You can tell basically because when the sun is to the south, the ITCZ is stronger to the south, with the Indian Ocean and the so-called South Pacific Convergence Zone. This is actually the ITCZ, which is very weak when the sun is to the south, and the rising motion is moved to the south compared to the summer months. You can see that in the summer, as the sun moves north across the equator, ITCZ gets shifted to the north, gets much stronger, so the entire system is moved. And you can clearly see this cross-equatorial transports happening seasonally. But you can see now the drop in the tropopause because of colder temperatures at high latitudes and volume of the atmosphere shrinking, and you get these complicated cells that we talked about. And you can see the convergence as well. Okay, and you can see the split of the ITCZ because of the monsoon circulation here. Clear cross-equatorial southwesterly winds bringing lots of moisture, but the ocean is warm enough that it holds on to the ITCZ, so you get marine ITCZ and continental convergence zone over the Indian Ocean. So complicated dynamics which are hidden when we do zonal averages and look at this. Okay, so if you open it up, then you obviously see the complications associated with it, but you also see the mid-latitude storm tracks and rainfall amounts being larger there, corresponding to these cyclonic systems. The same thing in the Mid-latitudes, I won't go into this. This is just showing the ITCZ, but misses again the complications over the Indian Ocean. I missed one figure here, which I will add a little bit later. Essentially, it shows mid-latitude storms as well. I will show that in a minute when I finish this. So before going to ocean circulation, maybe let me add that and pause. Let's add the upper level flow to this because it tells you better how to understand the seasonality. So just to look at the upper level flow, not near the surface as we saw with the trade winds and so on, and the ITCZ, upper level flow shows lots of these small scale systems, especially in the mid latitudes where the flow is incredibly strong and it is westerly even in the upper levels. But you can see it's much stronger here than here. It's weaker here and stronger here. So that should tell you something about the seasonality. For example, when the sun is to the south, the equator to pole temperature gradient here is stronger. So the jet stream and the mid-latitude westerlies here are stronger. Okay, so that's associated with the more energy transport needed as well. And the Hadley cell is weak, so you see weak flows here in the upper level. So in the lower level you have convergence, in the upper level you have divergence, so generally weaker. But you can see that in the summer months, boreal summer months, when the gradient is stronger here, you see stronger westerlies here and more wobble, and weaker westerlies here with the whole system becoming weaker. But you see strong cross-equatorial flow in the Hadley cell because the ITCZ is to the north and very strong. There is cross-equatorial flow happening to supply the Hadley cell, right? So you have very strong cross-equatorial flow happening. So upper level flow is also cross-equatorial, you can see here clearly, and that is seen clearly here. So this is how energy gets moved back and forth across the equator by the ITCZ, which is referred to as the energy equator. Okay, so typically you should be able to comfortably say these basic things of connecting equator to pole temperature gradients to seasons, to atmospheric circulation, to ITCZ, to the seasonality of the monsoon rainfall, and so on and so forth. So without getting into details, that should be possible, and it tells you that you have understood enough of the atmospheric circulation that is needed for this course or for any other climate related research you may be doing. You may not get into all the atmospheric dynamics, but you'll often need atmospheric dynamics to interpret your hydrology work, your extreme rainfall work, and so on and so forth. So it's good to know these basics.